is 0. So in other words, when I take, okay, this tape is, it says integration of the power rule. What it means also is antiderivative. The current way we say this is antiderivative because we're kind of going backwards of the power rule for derivatives. But the power rule says add 1 to the power, and then whatever that new power is, then you place it in the denominator, in plus c. Now, one reason we call it antiderivative is because if we took the derivative of this, which would mean I would move that down, I would have n plus 1 divides out this n plus 1, and then that would leave me x to the n. And the derivative of a constant is 0. So in other words, when I take the derivative of this, I would end up back having this. And so it's the antiderivative. And another concept in here is that you really shouldn't have to have the answers in the back of the book for integration or for antiderivatives. Because if you'll take the derivative of this and it comes back to what you had to start with, then you have to correct. So the power rule, one more time, is add 1 to whatever that power is, and then place that new number in the denominator, plus c. In antiderivatives, in integration, this is what this symbol is saying to us, is we always put a plus c on, I'm going to use another term, indefinite integral. This is the indefinite integral because it's not definite because we don't know what that c is. It could be 0, it could be 5, it could be -2 or whatever. So this is also called in calculus books the indefinite integral. Integration, antiderivative. All right, now let's look at examples. In your notes, we have this, the integration, or the antiderivative, or the indefinite integral of x squared dx. Now, the dx is very important. It's telling us this is the letter we're going to use the power rule on. So that will be very important when you go on into calculus a little further. So, the answer to this then would be x to the 3rd power divided by 3 plus c. Simply add 1 to the power, place that new power denominator. Alright, so let's go to the next one. So this would be x to the 5th over 5 plus x to the 2nd over 2 plus c. Now, this is a technicality we need to pay attention to. You will see in the textbook a lot of times this in parentheses. What they're saying is that you distribute the dx to both of these. You really should have dx times the x and dx times the x to the 4th power. In other words, when you have the integration or the antiderivative or the indefinite integral of x plus x plus x plus stuff, then you just simply do the power rule for each part. All right? Next example. Next example says, okay, what happens if we have a number in here, a constant? Well, we don't pay attention to that. We simply come along and write that down, and then we do x to the power rule of the x plus c. Now, another way of doing this, and I think it'd be wise for you to see this now, I'm going to show it to you later, is you can factor out constants. If a number's in here, you can factor it out just like a regular factoring. Then you can take that out and come in here and say, okay, then it's 5 times whatever's out in front times what the integration of this is. And then if you want to, you multiply that back in there and you come up with what we had to start with. All right, next one. The integration of a constant. Well, the integration of 6 is 6x plus c. Why? Because what is the derivative of 6x? Well, it's 6. So the integration of 7 is 7x. The integration of 1 over 5x is, 1 over 5 is 1 over 5x. So the integration of any constant is simply that constant times x. Now we could do that by reasoning, by rule, because this is like x to the 0 power. As long as x is not 0, anything in the 0 power is 1. So we can consider this as x to the 0. So if I add 1 to that, I get 1 over 1. So just know that from now on. The integration of constant is the constant times x. And don't get confused with fractions and stuff. In other words, if I come over here and say this is x over 5, then the integration of that is 1 over 5. Then this is simply the x up here over 5. Okay, let's look at the next examples. Now I hope you'll hear this and remember. In Calculus 1, you only have one rule of integration, or antiderivatives, or indefinite integral, and that is the power rule. Now, if you go to Calculus 2, you have to learn about 26 other ones, but here we only have one rule for integration, for antiderivative, and that is the power rule. So therefore, the first step, either mentally or on paper, is to write down this is the integration of x to a power plus x to a power plus x to a power x to a power. In other words, you change it either mentally or on paper and write x to a power, x to a power, x to a power, x to a power. And now you integrate. So this would be x to the 4 over 4. And put an equal sign there and keep it in order. You're saying that the integration of this, the antiderivative of this, is equal to, and then x to a power, and so that power is 1.5, which is 3 halves, and then x to a power, and then the derivative, antiderivative, of a constant is that times that plus c. So change it, x to a power, x to a power, x to a power, x to a power. Since this is dx over here, then we're going to raise the powers of the x's. Now, another thing to notice, in a problem like this, learn to do this to start with. This is 3 halves. If you divide by a fraction, you invert and multiply. So that 2 will go up here. So when you see an answer in the back of the book or something, and you see it like this, you need to have seen in your mind that what they did is they took that fractional power, inverted, and multiplied. Now, the other thing that you need to be able to see is if this x to the 3 halves is x to the 1 1/2, and so that's x times the square root of x. X to the 1/2, 1 1/2. So in other words, you might see this written for a final answer as x times the square root of x. You need to just see those things and see what's happening by knowing your power rules from algebra. Okay, let's go to the next one. Okay, again, the first thing we do is rewrite this x to a power, x to a power. Now that's the 1/2 power. It's on the bottom. When we move it up, it changes it to a negative. And this is 5, still minus, to the 3rd power, x to the 3rd power. and this is the square root of 5, and x to the 1/2 power. In other words, you can split this as the square root of 5 and the square root of x. And what I'm trying to say here is that at this point, we must keep these numbers separate, because all we can do is x to a power, x to a power. Okay, so I'm going to split this and split that, and I have x to a power. So this is now x to the 3/2. So it's 3/2 over 3/2. And this is plus 2, x to the plus 1/2 over 1/2. Right? But what that ends up doing then is inverting and multiplying, and you will see a 4 up here. Right? Then this is a minus 125, excuse me, 125 x to the 4th power over 4. We're going to, don't do the power on the number. Okay, that still is 5 to the 3rd power. Okay, then plus the square root of 5, x here again is the 3/2 over 3/2. Plus c. Okay, now I'm going to show you a little later how we could have done this a little different. Okay, but right now the concept is to get something to a power, power, x to a power, x to a power. If you have numbers with it, kind of get those out of the way. Just keep them there times that, and so it just comes back this times whatever you have, this times whatever you have, this times whatever you have. Okay, now let's go to the next concept that you need to understand, and that is, in integration, in Calculus 1, there is no such thing as a product rule or a quotient rule. So if we have products and divisions and stuff like that, we cannot do Calculus 1 anything except change it x to a power. So what we're going to do here is take this and do multiplication, so that's now x squared plus x minus 2 dx. And now we integrate power rule, x3 over 3 plus x2 over 2 minus 2x plus c. So the rule is we have no product rule in Calculus 1. So we must change it and have it x to the power, x to a power, x to a power. And then we use the power rule. All right, next example, we have division. Well, what we have to do is first change that. Now listen close to this. This is a rule that comes into play a whole lot of places in math. And that is, if you have a single term, you don't have any plus or minuses down here, you have a single term in the denominator, then you may place each part over that denominator. And separate it. This is very important, partial fractions and other places. But the concept is if I added these fractions back together, I would have that. So really all you're doing is splitting a fraction back apart. In other words, if you have 3/5 plus 7/5, that's the same thing as 3 plus 7/5. So we're just splitting it back out. Then we change this to x to a power, x to a power, and then we take the antiderivative. So this would now be 3x to the minus 1 over minus 1 plus x plus c. Now at this point, a rule in my class, and I think it's a rule in most classes,
is that you never leave anything to a negative power. So when you put a final answer on this problem, move the minus power back down to the denominator. So this problem could look like then a minus 3 over x plus x plus c. And if you have a minus down here, learn to move it out in front or on top. Don't leave minuses in the denominator fractions. Okay, so that's the concept of division. All right, so let's look at another example of it. So what we have here is a single term denominator. Therefore, we rewrite this as x to the 4th over x3 minus 1 over x3. And then that's rewritten as x minus x to the minus 3. Now we have power, so the answer is x squared over 2 minus x to the minus 2 over minus 2 plus c. Now learn to change that. Okay, so that minus that times that minus will make final answer a plus. And this x to the minus 2 moves down to x squared. Now when you have this in application sometimes, you might want to get a common denominator and stuff like that. And that's why you need to learn to move negative powers to the denominator. Okay, next example is, again, no product rule. If you have the integration of this times this, then what you must do is add the powers. Now this is to the first power, and square root is to the 1/2 power. And if you multiply bases that are same, then you add the powers. Okay? Now better have a dx there. So therefore the integration of that equals x to the 5 halves over 5 halves plus c. Point being is that you need to multiply those together to get to a power. Okay, let's take now another example. Here's one. Now, this is not a single term denominator, so therefore you use long division. Or you use algebra and factor. The point being, listen closely, the point being is you've got to do some kind of algebra to get it to be x to a power, x to a power, x to a power. Whatever it takes, algebra concept, then do that. Right? So now when we integrate this, this is simply x squared over 2 minus x plus c. All right. Now we're going to start process what I call David Copperfield's magic. Now, power rule. If you power rule a parenthesis, I'm going to say that I don't have any time, I want you to hear that. The power rule of a parenthesis, the power rule of a parenthesis, we're power ruling the parenthesis, not what's inside. That just automatically goes with it. We're going to power rule the parenthesis. So if I want to power rule a parenthesis and call it, so I'm going to add 1 to the power and put that new power in. But listen. To do that, we must have the derivative of the inside of the parenthesis. We must have the derivative of the inside of the parenthesis. So the derivative of that is 5. Well, I'm going to put a 5 in the problem, in here. But to do that, I must put 1 over 5 out front. It's reciprocal. So I placed in the problem just a 1. I have not changed the value of the problem. This times this is 1. Now, when you have the derivative of the inside of the parentheses over here, then you may power rule the parentheses. When you have the derivative of the inside of the parentheses over here with the dx, then you may power rule the parentheses times whatever you had to put out front. And this just disappears. That's the David Copperfield. That just disappears. And all you do is power rule the parentheses.
All right, let's go to the next example. All right, next example is a parenthesis to a power. A parenthesis to a power. Quit looking at that right now. We have a parenthesis to the power. Now go look at the inside, and what is the derivative of the inside? The derivative inside is 1. We have it. We have it. Therefore, the answer is the parenthesis power rule. All right, next example. We have a parenthesis to a power. A parenthesis to a power. Now, what is the derivative of the inside of that parenthesis? Well, it's a 5. So I'll go put a 5 here, and I have to put a 1 over 5 out front. And now the answer is whatever's out front times the parenthesis to the power rule. I don't care what's in there. It's power rule of the parenthesis. So I'll just copy back what was inside. Okay, let's look at some more examples.
Okay.
All right, I have a denominator. I must move that denominator up. So this would be the integration of the parenthesis to the minus 3 power. Okay, so what is the derivative of the inside parenthesis? Well, it's a. So that means I need an a in here and a 1 over a out front. Therefore, the answer to this will be 1 over the a out there. The parenthesis to the minus 2 power over minus 2 plus c. Move the parentheses up. Power rule of parentheses. The derivative of the inside of the parentheses is a, so I must have an a put in here. Got to do its reciprocal out front. And so what I have now is this out front times the parentheses to the minus 2 over minus 2. Be careful on this. After practice of derivatives, some students will make this a minus 4. Just be careful. Remember, integration, you have to add 1 to it. All right, now for our final answer, don't leave that to the negative power here, move it down. So what we really have is a minus 1 over a times the parentheses to the second power. I'm sorry, get 2 down here. Don't forget this negative, I move up to the top or out front. The a is on the bottom here, the 2 is on the bottom here, and then this moves down. So there's the answer. All right, now let's look at the next one. And don't get caught. Don't just make all parentheses work. For instance, what is the derivative of the inside of this parenthesis? Well, it's 1 over 2 times the square of x. You cannot place x's into the problem. You can only place a constant and put its reciprocal out front. Therefore, this one has to be multiplied out. So multiplying this out, the first times the first is x. First times the second, double, is 2 times the square root of 2, square root of x. And the last one squared is 2. And now you integrate. So this would be x squared over 2
2 times the square root of 2, x to the 3 halves, over 3 halves, plus 2x plus c. All right, so in other words, this example is say, don't force it, don't force it. If you don't have a grid inside and cannot get that by placing a number here and its reciprocal out front, then you just have to do the algebra and get back to x to the power, x to the power, x to the power. All right, now let's look at the next example, and this is one that David Copperfield comes into play. A lot of students get this confused. All right, I have a parenthesis. I have a parenthesis to a power. That's what I'm looking for. So if I have a parenthesis to a power, I look for everything around it to be the derivative inside. So the derivative of the inside is a minus 2x. So I will multiply this by minus 2 and put a minus 1/2 out in front. And therefore the answer is a minus 1/2. The parenthesis to the power rule. And there's that David Copperfield thing. This just disappears. Now let's take the derivative of this. If I take the derivative of this, I move the 4 out in front, it divides out, changes that to 3. And then I have to take the derivative inside. The derivative inside is a minus 2x. So if I take the derivative of this, it comes back to what I had to start with. All right, next example. Next example is, you have a denominator, you're supposed to move it up. I'll put this in parentheses, put this in parentheses, to the minus 1/2. Now, what is the derivative of the inside of this parenthesis? Well, it's 2. Now, more than that. Hey, don't use that. What is the derivative of the inside of this parenthesis? There it is. Therefore, it's the power rule of this parenthesis. And that just disappears again. All right, next example. I have parentheses in the denominator, so I move it up. So this is x squared. 1 minus x cubed minus 4. The derivative inside is a minus 3x squared. So it's a minus 1/3 times the parentheses minus 3 over minus 3 plus c. Denominator, move it up, right to a negative power. Check the inside of that parenthesis. If we can make everything around it, the derivative of that is the power rule of the parenthesis. Power rule of the parenthesis. Okay, the notes show you you're supposed to move this back down, move this minus through that minus, and you have 9 down here. And this to the 3rd power. Okay, so take the next example. Have a parenthesis. Derivative of that is a 2x. No, I got more than that, so that's no good. The derivative of this is 3x squared plus 3. 3x squared plus 3. Hey, that's close. So what I'll do here is multiply this by 3 and put a 1/3 out in front. It goes back to the Peirce rule. The Peirce rule is if you make it work, then do it. Okay, whatever it takes to make it work, as long as it's morally, ethically correct, then get the job done. Right? So what I can do is multiply all this by 3 and then multiply here by 1/3, and I've not changed the value of that problem. So now I have the derivative inside of this, therefore it's the power rule. Look at that one for a few minutes. What I'm saying to you is if you have kind of like two parentheses multiplied together, there's no such thing as a product rule. So one thing to look at is if one of these is the derivative of an inside of the other one, then I can power rule that one. Well, if I can make it that way by legal algebra steps, which simply means I'll multiply top of 3 and the bottom of 3, and therefore I have that. Now I can power rule this parenthesis. All right, let's look at the last two examples. The next example is the same concept. What we'll do is write that down and move the bottom up to a minus 1/3. Remember now, whatever that root is the denominator. Whatever the power of all this is the numerator. Now we drew it inside. There it is. Therefore, all I have to do is power rule. Parenthesis. And again, Copperfield disappears. Now don't come back and try to write down. I have students all the time trying to come back and write the answer as another parenthesis. There's some kind of a product rule here. That just disappears. You don't have it in the final answer. Because, let's take the derivative of this. If I take the derivative of this, I move the 2/3 out. Subtract 1 from it. And then take the derivative inside. And that's what I'm going to start with. So I did it correctly. All right, last example. The last example is saying, look, pay attention, pay attention, pay attention. That's important. The integration of this, the antiderivative, is that if I'm taking the integration with respect to y, then this is just a constant. That's just like the number 4. What is the integration of 4 dx? It's 4x. What's the integration of 4 dy? It's 4y. So the integration of this with respect to y that's just a constant. And there's the y. So that happens to be very important. All right, this concludes in the beginning concept of just the power rule for, again, integration or indefinite integral because of the plus c, or antiderivative. Antiderivative is a better word. It's just I want you to make sure you've heard all three. So this concludes this statement.
cold.
Under anesthesia, some of the body's systems of adjustment are switched off. We can't keep warm. Sweating. So operating rooms are crammed with artificial systems that adapt for us. Meeting each change with an appropriate response works for machines, too. Feedback systems monitor what's happening and tell machines how to react. Less work for people. No need to tend machines that tend themselves. One way or another, we all depend on feedback. Åsa Kroon lives in a small town in Sweden. She's like any 10-year-old girl anywhere, with one exception. Åsa was born with part of her right arm missing. When she was 3, her parents insisted she be fitted with an artificial arm. Doctors told them she was too young. It had never been done, couldn't be done.
Even if all of us were telling that it was impossible, nobody seemed to have really tried it. Of course, it could be very difficult teaching small children to move the hand, but the first trial showed that also after some few minutes, really were able to open and close the hand, taking papers, giving from one person to another. They learn by themselves as they learn to walk.